So, good morning and welcome to the second class of Discrete Mathematics. Today we'll have two things to discuss at the lecture, or maybe two or three. So the first one will be about the first home assignments. So in general, we shall have three home assignments which will be incorporated in your grade. So there will be two of them will be programming, and this will be the first one. And the first and the third one will be programming, and the second one will be written just like midterm. So just take home exam. Let's start with a discussion of that. On the page of the course, and I posted the link on Teams, I will also show it on the screen today. I will post all the technical information about how to submit, some examples of code which are related to this home task, and stuff like that. Today, so yeah, beware, on the page there is some material from the previous year. Some of that is outdated, so do not use it. Basically, say the links to GitHub. I will do a new setup for today's class, for this class, so not to mix with the older students who were a year ago. So today I will just discuss the ideas behind it and what is the formulation of the task. What is it about? So it's about resolution method, and also it's a bit connected with formal language theory and parsing of using context-free grammars, but we'll discuss it today. Question.
Resolution method on Russian.
Метод резолюции. The same. Метод резолюции. Okay. So we are continuing discussing satisfiability of Boolean formulae, satisfying assignments assigning zeros and ones to variables, and if it makes the formula true, then it is a satisfying assignment. And satisfiability is a model of a very general situation of finding, or more precisely, checking for existence of an object with given properties. In Russian, so satisfiability — это выполнимость, assignment — набор, выполняющий набор, satisfying assignment. And we recall that resolution method with resolution is a method of determining whether a Boolean formula given in conjunctive normal form is satisfiable. So this is a method which is in general not so efficient, but in some cases it will be more efficient than just a brute force, trying to find the satisfying assignment by brute forcing over all possible assignments. CNF conjunctivно нормальная форма. A conjunctive normal form is a conjunction of clauses. Each clause is a disjunction of literals. So this is an example of a clause. You have negative for x and z and positive for y. A clause could include only part of the variables. It is not required to include all of them. So some of them could be missing. And this means that it is relevant to them. And the algorithm applies the following resolution rule. If you have one clause with P and another with a negation of P, then you can remove them and unite these clauses into one. And this is called the resolution rule. It's sound, meaning that if the premises are satisfied, those on top of the line, then the conclusion is also satisfied by the same assignment. So adding new clauses by applying this rule does not affect satisfiability. The same assignments will satisfy the original formula and the original CNF and the new CNF, which is obtained from the original one by adding new clauses using resolution. So here is the web page of the course. It's not a presentation actually, but let me just quickly show up the presentation itself. So we recall that we're talking about satisfiability for Boolean formulae. Satisfying assignment is an assignment which assigns zeros and ones to variables, which makes the formula true. And in general, it's a model of checking for existence of an object with given properties. And recall that the resolution method is a method of determining whether a formula is satisfiable. And it's based on, so it's a conjunctive normal form, so there is a conjunction of clauses. And there is a rule which allows adding new clauses which saturate the conjunctive normal form without affecting its satisfiability. So satisfying assignments are still valid.
This form between A and
or
P and B or not B is there.
No, there are just two. So we have two clauses and we replace it with one. So what is a CNF? It's a conjunction of clauses.
Yes.
We understand it as, say, a list of clauses. And we add new clauses using this. So if in this list we had...
Can we write conjunction between A and...
Yes, you can write conjunction between these two, yes. So which is... They're just a list, they should be satisfied simultaneously, so it's a conjunction. Okay? So this is how it works. Adding this new clause does not alter satisfiability. So you can easily check that if both on top are satisfied, then the bottom is also satisfied by the same assignment. So it's just adding new redundant clauses. But what's the idea? If we obtain an empty clause, which corresponds to being false, just constant false, then that CNF is not satisfiable, because just the resolution rule keeps validity. It's, as I said, it's, you cannot satisfy this, it's false, and therefore you could not have satisfied the original one. And moreover, there is a completeness theorem. This is a criterion that if you cannot obtain this, the false clause, the empty clause, then the CNF is satisfiable. And we'll prove it today. So, however, if you cannot derive the empty clause, it does not give us the satisfying assignment as it is. So it just says that there's such an assignment exists, but it does not usually. Sometimes it gives us, but sometimes it doesn't. When does it give it really? If we obtain isolated variables. So suppose we proceed by a resolution and we obtain a clause which contains just one variable, say p. Then this enforces us to make p true, because you have to satisfy the whole CNF. In particular, you have to satisfy this clause, the clause p. And in order for this clause to be satisfied, you need to make it true. Or if you have not p, you will have p false. But sometimes it doesn't hold. We saturated, we didn't obtain false, and we didn't obtain an isolated clause for some variable, neither p or not p. And this means that we have to do something extra, because then probably both p and or not p could be true, but there could be other constraints. So for example, you could have just p or q, or p or not q. This makes it, you cannot make p false and q true. But so this method solves the decision problem, yes or no, satisfiable, not satisfiable, but it doesn't solve the search problem. So this is the difference. If you're lucky enough, as I said, you can have isolated clauses, and then you are dictated what satisfying assignment should be, but it's not always the case. And if it's not the case, we can consider the following thing. So suppose you have a CNF which is saturated, so you applied all the resolutions, and you didn't obtain false. That means that you didn't come to contradiction, and also you didn't obtain the negation of x as an isolated literal. Then you can add x, and you are still satisfied. So you don't have an isolated literal which forces x to be false. Then x is allowed to be true. And the same if you don't have x, you are allowed to make x false. Okay?
So we can add x and, for example, kill some not x's in...
Yes, yes. This is what is going to be next. So in particular, if S is satisfiable, not satisfiable, yeah, it's satisfiable, so it's a saturated CNF, it's not non-contradictory. And also it doesn't include after saturation x or not x, you can make an arbitrary choice for the value of x. So if you are not enforced to make x true or x false, then you can just say voluntarily, say, okay, x should be true, or x should be false. This is my decision. It's not the decision of the CNF. And then, but after that, it's not saturated. Then what's going on? It's exactly saturated, насыщенно in Russian. It's exactly what you are saying. So then you should again proceed by resolution. Using this x, you could kill not x's in other clauses. There could be more isolated literals after that. So for example, you added x and you had to say y or not x. It will give a y. So y should be now true. And so on and so on. Yeah, so this you have to saturate it again after this arbitrary choice before considering another variable. So this is an example, yeah. So this is a saturated one. here is a CNF where you cannot apply any resolution because there are two clauses and there is no resolution applicable. But you can choose x equals 0 and add not x. And this will immediately dictate the values for x, y, and z. Because this will give you not y and z, and you will have y equals 0, z equals to 1. So this is after one choice. So at one time you have the right to choose voluntarily, but then you proceed by resolution and everything else is fixed. So how to prove this? Well, it's easy. So indeed, suppose it does not include not x as an isolated variable. And we have to show that applying new resolutions will not give us contradiction. Indeed, the new resolutions, they should involve this. So we added x. And the new resolutions should involve this x. Otherwise, they could have been applied before. Because this is the only new element which we added. This procedure alters satisfiability. It does not, x it's a new, it's not, doesn't follow from the original CNF. And therefore, if such resolution generates false, then there should have been the negation of x in the original S. And this is not the case. So this is an easy thing. And this is an example how it works. So consider this CNF. We proceed by resolutions. I will not go into details. I will post the slides on the, they are already posted on the web, and you will see that these this is actually applying possible resolutions to the original formula. We apply more. We apply more. So you see here this is a big growth because we have 3 clauses they allow to be. But by the way, there's still 3. There is no 4. It could have happened, but it doesn't happen. And now we see that here there is one isolated literal, which is you see this blue P on top on the right. So it was actually there in the original CNF. It's an isolated literal. But for S, we applied all possible. For S, R, and Q, we applied all possible resolutions. We don't have isolated literals. Therefore, we're allowed to make arbitrary choice, say for S. And I say that S should be true. I dictate it. And the proposition which we just proved, sorry, it shows that. So this shows that this S is independent from the CNF, and you are allowed to add S. You could also add not S, and it will give you another satisfied assignment. But after we added S, we have Z, T, and all of this is obtained by resolution. So for example, here you have S, you have not S or Z. So you will have T, the same somewhere here for not S or T. Also, something else is added, which is not needed for us. But actually now we already know what happens. So we have P, S, Z, T, but we do not know about Q. And then the process can go forward, and then we'll also we saturate it, and then we can make the arbitrary choice for Q. And after that, we obtain the satisfying assignment.
We saturated conjunction form.
Yeah, it's all a big. It's the commas here are conjunctions.
With add S.
We added S. We added S as a new clause, so we modified it. And the lemma which we proved here, it says that if we don't have, we saturated it without S, then we know that we don't have the negation of S here as an isolated literal. This means by this proposition that we can add S, modify our CNF, and it will still be satisfiable. So there exists a satisfying assignment where S is true. And then we add S, and then we continue applying resolutions. We continue the saturation process. And this gives us Z, T, and stuff like that. And then we do the same for Q. I didn't write it down here, but we can do it.
But add Q, yeah?
For example, Q or not Q.
Yeah.
So for example, we add not Q, but basically here you can already stop and just do it manually, because you know P, S, Z, T, we don't know Q, and just check, let Q be 0, and check that this is satisfiable, for example. So if Q is 0 and all these are true, this is true. It's also we have R, sorry. So, okay, this could be an interesting thing. So suppose I make Q false. Now what happens? I will have, this is true, this is true, this is true, this is true, but this one, the second, it's not R or Q.
Can we just say R is equal to 0?
And yeah, then R, so, but if you make Q equals 0, R should be also 0. You cannot make it 1, because there is this disjunction which should be satisfied. Or dually, you can say that Q is true, and then you are fine. R is arbitrary. Because if you say that Q is true, then you satisfy this clause, and R is irrelevant. You can make it. Чтобы прийти к противоречию. We're saturating in order to... So how do we check that... как мы проверяем, что наша нормальная форма выполнима или невыполнима? We use resolution. If we obtain contradiction, empty clause, then it's not satisfiable. If we don't obtain empty clause, how do we check that we cannot obtain it? We just apply all possible resolutions.
Еще получаешь новые скобки и можешь получить еще изолированную переменную, а дальше уже тут работать.
So here, for example, if we have a S, if we make S true, then immediately you have Z and T also true by applying resolutions. You cannot have both S true and Z false, because then this clause will fail. Okay, more questions? So, special case, it's 2 CNF. So, if the clause includes at least 3 literals, then you can grow it. You can have 4 and more. And this could lead to exponential blow up. And so the saturation in general is potential exponential procedure. So you can possibly have too many clauses, and this will make you inefficient. But if you have a 2 CNF, which means that each clause includes no more than 2 literals, the clauses do not grow, because if you resolve 2 clauses which include 2 literals each, then the result will include at maximum 2 literals. Here is an example. But why at maximum? Because possibly they could coincide. So they could be, say, X or P and X or not P. And this just says that it's X, just one. Or it could be false, which means empty. So it means that you just apply go to contradiction. But the key idea is for 2 CNF, you don't have exponential saturation procedure. And this is the polynomial upper bound. We see it last time. And the saturation process is polynomial.
One question. In previous lecture, say that resolution method for 2 CNF generated 2 clauses.
It means, yeah, it generates two dash clauses. So it means clauses which include only 2 variables. So the number of clauses is as follows. So 1 empty, 2 and 1 literal clauses, because it's either X or not X. And 4n square, it's a coarse upper bound, but it's still polynomial. It will be still quadratic. It's where you have 2 literals. This doesn't take care about the order, which can be reordered. They could coincide. You can also have the X or not X can be ignored because it's always true. But even here. And now you can organize your saturation process as follows. You take a clause from the list, starting from the second one, and try to resolve it against all the earlier ones. Okay, so you have the list of the clauses, and you say resolve the second with the try to resolve if possible. Second with the first, then the third with the second and the first, the fourth with the third, 3, 1, 2, 1, etc. And if you get a new clause, then you append it to the bottom of the list. You write it on the bottom. And then in this process, at some point, you will reach it and also try to resolve it against everything which is above. Clear? So this is the procedure. How can you organize saturation? Any 2 clauses in your list will be at some point tried for resolution. So this means that if you run out of clauses, and you will run out of them because there is a total polynomial number of them, it's a finite number of possible clauses. At some point, at this point, your CNF will be saturated. And at that point, when you finalize this process, You will have a list of clauses which is saturated, and what you do. If there is an empty clause, well, once you reach an empty clause, you say contradiction, fail, not satisfiable. But if you don't have this bottom empty clause, you say that first it is satisfiable, right? And second, you say that you can find a satisfying assignment. You seek for one element clauses, which are isolated variable, isolated literals. You know the assignment for them. If for some p you don't have isolated p and don't have isolated not p, you just add, well, arbitrary. For example, always add true. Always add that p should be true, or always add false. It's by your choice. And then you append it to the bottom of the clause of the CNF, and you apply again all the resolutions. So you try to resolve it against everything on top. You get new ones, resolve. After applying all the resolutions, you again get, now you never get contradiction, because you know that your CNF was satisfiable, and you added variables only in safe ways. But finally, you obtain isolated literals for all variables, and this yields the one satisfying assignment. It's not the only one, because you made arbitrary choices sometimes. Yielding all satisfying assignments, even for two CNF, could be exponential, because just the number of them could be exponential. You can say, for example, a trivial CNF which is satisfied by anything. It has 2 power n satisfying assignments, right? So it's exponential procedure just because the answer is exponential. But finding at least one is polynomial. And this satisfiability for 2 CNF will be your task for homework number 1. So the easy part, the easy version, say baby version, is to check satisfiability using resolution methods. And the full task will be checking satisfiability, and if the answer is yes, to return one of the satisfying assignments. And as for grading, well, it will be all posted on the web page. Well, it will the full task will cost the full grade for this task, and I think it will be like that. So it will, you have 10 you have points out of 10 for your home assignments, and they will be like it 4, 4, 2. So the first assignment has 4 points maximum. The second also, and the third one will be easier, it will be 2 points. And here, if you do only the easy version, you will have 2 points. If you do both, if you do full version, you will get 4 points. It's how it works. And also there will be rules about the deadlines, which I will not speak out now. They will go to the web page. I will just post it there. So you could have a reduction if you miss the deadline as usual. So it's standard. So so the easy version is just applying resolution, and the full task is applying resolution, then adding variables for which we didn't obtain isolated literal, applying it again. So this will be a home task, but the important thing about this home assignment is that the input should be given in a human readable form as a string representing the formula. So it's not like you say, okay, I will just take a Python code and hard code, say the CNF as a list of lists of something. No, it should be a human readable string, so it should have a good interface that the human inputs it's inside and checks it. Well, it will be all the testing will be automatized on GitHub, so you will have this specific rules of how you submit the input date. It will be all documented in the README, so I will not go into these details now. But the idea is that the input should be a string of symbols which is represent a formula. So yeah, so how it should be implemented. So it will be 2 functions, first of which should return true or false, and the second should return the satisfying assignment. This will all be on GitHub. So these are the, also what is going on, some extra addition for you, that besides disjunctions in clauses, you will be allowed to have elementary implications. Literal, arrow, literal. Well, you know that this does not add too much, because A implies B is not A or B. So implication is also a form of disjunction, right? Classically, of course. And they will be encoded like this, just to make it in ASCII standard code. So it will be, conjunction will be just slash backslash, disjunction backslash slash. The tilde will be for negation, and minus, this is the arrow, so minus and greater symbol. Just not to mess up with, say, Unicode or something like that. So literals will be either X or not X, X is a variable. Variables are arbitrary letters, so X, A, B, P, Q, etc. Letters. Clauses will be like that. That it's either disjunction of literals or an implication between literals, which is also a disjunction. So it's not L1 or L2. And the CNF is a conjunction of clauses, which are in brackets. And the first thing in which the program should do, it should translate the input into a machine digestible form. And this is called the parsing of the input. So this is the grammar for CNFs. So this is a formal expression which exactly reflects their informal definition before. So it says this: a CNF is either a clause or a bigger CNF conjunction clause. A clause is either it should be in brackets, and it's either disjunction of literals or implication of literals, and the literal is a variable or negation of variable. So it's just it's a formal notation for the same which we have seen here, right? So this is informal and this is formal, so it's the same. And we shall use, or you are saying, encouraged to use specific software, which is called PLY, which is Python, Lex, and Yak, to automatize the parsing process. So you should not write the parser by yourself, just from scratch, but you can use specialized things for that.
Is the part grammar for CNF?
Existed грамматика для конъюнктивных нормальных форм.
Вот, то есть такая... Я понимаю... Нет, я не понимаю. Ладно, что это?
This is a formal representation of the definition of CNF. So here we say that. What is a CNF?
We must define...
We define what strings of symbols are valid CNFs. Here this slide is understandable, right?
Yes.
So the next slide will be the same but formally. So what is that? What is a CNF? A CNF is a conjunction of clauses, right? What is a clause? A clause is either disjunction or implication of literals. What is a literal? It's either variable or it's negation. The same is written here. Just what is a CNF? CNF, by definition, is either a clause or conjunction of clauses. A clause is either this or this. A literal is either this or this. And what's a variable? Well, it will be in the lexical part. It's just, well, this is just the same. Of course, well, unfortunately, in this course we don't have time for, talking about constructive grammars in detail. It could be a topic of a specific course. But I just wanted to emphasize that this is just the same, which is written in a formal way. It's just syntax for the informal thing there. And the good thing is that this syntax could be embedded into Python, Lex, and Yak, and the system will automatically give you the parsing software for that without any interaction with the human. We'll see it right now. So this is the workflow which we're going to do. So we have the input string, which is just a string of symbols. It goes to a lexical analyzer and will give a stream of tokens. I will see what a token is in a moment. Then you go to syntactic analyzer or parser, and it will give you a recursive structure, which is machine readable or machine digestible representation of the formula. So here is an example. Well, I will not spoil the homework, of course. So I made up another example from the language called C. This is a program in the language C. And you input it as a stream of symbols, just one int, space, stuff like that. And then you replace it with tokens. So first one is keyword integer, then this is identifier called main, just the bracket. Bracket is very important, so it's a specific token. And tokens are much more convenient to work with, unlike just symbols. So for example, in our grammars, probably this implication is going to be just one token instead of being two matrices, because logically it's one. And
sorry, Lex and Yak, is it only for Linux?
No, in Python. It's a library for Python. Okay. It's cross-platform software as everything in Python. So yeah, I will talk about this in a moment. But if the question arose, I will say it now. So Lex and Yak without this P, without Python, it's written in C or C++, it's portable, I think, also for say Windows or Mac, where you can use C, but it's a good old school say software which is just Python Lex and Yak is a version of Lex and Yak for Python, and it works everywhere where Python works. It doesn't use any specific machine-dependent things, so it just works on strings. It doesn't require some low-level programming. So suppose another task would translate just algebraic polynomials into normal form, like this. So you can see this, right? On the left, you have a polynomial which is written in sort of fancy way with brackets and stuff like that. On the right, you have its normal form. You open up all the brackets. How can you do it automatically? Well, this is the grammar. So it's maybe looks a bit scary, but here it says that an expression is a term minus term, expression plus term, expression minus term. So what is a term? A term is either a monomial or something in brackets, which makes more priority, or a term multiplied by an expression. We don't have multiplication sign here as in usual school algebra. A monomial is an optional integer, which is the coefficient here. Then we have x, which is the only variable. Optional power. Or it's just an integer. An integer means that it's a free one without x0. So optional integer is either an integer or empty. Epsilon stands for the empty string. We just put it here to see that this something here is empty. And the optional power is this power sign, and then it's integer also, or empty. It could be optional. And this is an example of the input. So the same encoded as formal string of symbols. Like in LaTeX, for example, you use this for power. So as you see that this is the implementation, lexical analysis is obtained by Lex. Parse is obtained by Yak, which is the background for yet another compiler. And we use Python, Lex, and Yak, which is PLY. So here we declare tokens, how the PLY code works. All this code will be online, so you will just, these are just examples from that. These are the literals. Not the literals of Boolean meaning, it's the literals of our thing. And then we declare a T function, which says that for each token, we say that, for example, if we have an integer, here we have as a command, this Python style command, which is a regular expression for integers. And then we say that we try, if we can convert it into an integer, then we put it into the value, now being not a string but an integer, real integer. If there is something which is erroneous, probably it's a too large, which cannot be translated, and we just throw an exception and return 0. So this regular expression. Another, for example, for names, we have the following regular expression. So the first should be alphanumeric or the underscore, and here we're allowed also to have integers or digits here. And then we build the Lex. So we import ply.lex as Lex. This to import this library, and then we run the Lex, and it will build all these finite automata for parsing, for lexical analysis absolutely automatically. We don't need to go inside. And for parsing, we have p functions, which are basically the same. So what is a p function? Here we, for example, when we have multiplication, well, this is just a helper which multiplies to polynomials. So polynomials in normal form are represented as just arrays of coefficients, right? And this is the way of multiplying them, just a code in Python. And then, for example, if we have this rule of our grammar, which says that a term is a term multiplied by an expression in brackets, we say the following. So this is the notation here. P of 0 is the result, and others are in this array are the arguments. So here you have the value of term, you have the value of the expression. You apply something, and you get the result. From where did you get this P of 1 and P of 3? Well, it is a recursive procedure. Your big polynomial, not in normal form, is defined recursively using our grammar, right? So suppose here we have an expression. This expression is a term, and the term is a term multiplied by an expression in brackets. This means that we can evaluate it by recursively applying our rules. So we've already evaluated these guys, and then we go. Okay, Okay. So this is going to be the code. So again, this uses this strange thing we have in Python that after the definition of a function, you can have just a bare string of symbols, which serves as a command. So Python actually ignores it when you run this function. But the PLY code, it analyzes our Python code and uses these as rules of the grammar and makes the parse as it. Makes it very convenient. So yeah, so it generates an object P0 using this P1, P2, and others obtained from the Alexa or from recursively from parsing. And now I build the Alexa again, like the parser, like the Alexa. So you import this library over Yak, and you just run it. So the courses and the everything is available on the course web page. And also, yeah, there are other examples like the calculator. This is for some special technical things. And then when you run it, you will what you will get. It builds the parser, so the program which parses, takes the input string, and runs and yields the result of the topmost element, which is the result of our. And you will see it in the so these are just some examples of the code, but you will see the whole code published there. So this is the end about definition for the homework. So good luck with that. Probably today or tomorrow, so fastly, I will post all the details on the web page. So the new things, so you can see everything in the already there in the previous year installation of the course. The only things which will change, of course, the deadlines, just because we started 1 week later actually than last year, so everything will be adjusted. And the links to GitHub submissions, which will be just renewed. So GitHub will be the basic way of submission because there is automatic testing, and you submit all the stuff in several seconds. It tests and gives you the mark and says, okay, either you are right or your program fails, and you have infinitely many attempts to fix it. So, and I don't see it even. You just commit stuff like that. So I encourage all people to get acquainted with GitHub and use it because it's one of the standard things in software development which people use, and it's quite convenient. If you have problems with that, problems could be strange. So last year we had some people, I think from Iran or somewhere elsewhere, just it's blocked out or something like that. In any problematic situations, you always have fallback solution to submit by email. It's okay. And then I will just run the tests on my machine and to tell the results. But as you can see, it's less convenient for me because there are many of you and I don't want to do any manual things using your code. And it's a lot less convenient for you because you have to wait for me to. And if I say that it fails, then you'll have to do another round, and this will make things slower. So the basic solution is GitHub. Also, you will have to submit by email if you use not Python or something else. It's not encouraged, but formally allowed because this is not a course in Python. If you program in other languages, please just then submit by email, and I'll try to test the code. Email, it's easier. So now we do some math, a completeness proof for resolution. So if one cannot obtain the empty clause by applying resolutions, then the CNF is satisfiable. So this is the hard part. So it's actually if and only if, right? So if you can obtain the empty clause, you are not satisfiable. This is easy. But the hard part is that if you can not obtain it, then you are satisfiable. This is unobvious because this means that resolution rule is strong enough to capture all possible contradictions. We prove it by induction of the number of variables. So first we establish it for 0 variables. Well, it's trivial. If you have no variables, you cannot have a contradiction, right? You have no clause. Or you have the empty clause, which is immediately a contradiction. And now you validate the step. So if you prove this theorem for n variables, we shift up to n plus 1. And this is mathematical induction. You show that it's valid always. 0 variables. So the only possible clause is empty. from n to n plus 1. So we denote this extra n plus first variable by p n plus 1, is q. And let S denote the saturation of our CNF. So we applied all possible resolutions. And now we take all the clauses which do not include not Q, and they could include Q, right? And we remove the Q. So we take all the part which does not falsify Q, and we say that this is S plus. So these could be satisfied with Q being true, because it does not include not Q, therefore Q could be true. And now we have S minus. These are all where you can make Q false, and you remove this not Q. So we say that take all the clauses without Q, which do not say that Q should be true, and remove not Q.
So divided like our S to parts.
Well, it's not actually two parts, because they could intersect. There could be clauses which include neither Q nor not Q, and they will be in both.
Yes. Okay.
So we take two subsets of S, which are
With Q and not.
yes. So no, without Q and without not Q, possibly with Q, and we remove the Q's from there. So, and both of them are of course saturated, because if you could apply a resolution in say S plus, you could also have applied it in S. And that's to show that at least one of them is satisfiable. So suppose both of them include false. What does it mean? It means that S includes both isolated literals of Q and negation of Q. Oh. This means that it includes both Q and the negation of Q, and therefore it includes false, because satisfaction, this contradiction. So this means that at least one of these is satisfiable. As it's not trivial, because we removed the Q's from there, and at some point it could have become empty, but it's not. So, and since both S plus and S minus do not use Q, they use only the first n variables, then we already know our theorem for this, right?
Yeah.
Because it's by induction. And the one which does not include empty, it's satisfiable, right? So if S plus is satisfiable, then we can take this satisfying assignment and let Q be 0. What happens then? Everything in S plus is satisfied, and everything else includes not Q, so it will be immediately satisfied by making Q 0, right? Mm-hmm. And if S minus, so because they're already satisfied, and these are satisfied like that, because Q, not Q1. And usually, if S minus is satisfied, we'll take Q equals 1. And it finishes the proof. Okay. So this is one of the not so many mathematical proofs of our course. Question?
Yes. So when we remove Q on not Q, we add Q and not Q, so it's like n plus 1 variables.
Yes. So we're it's this way of speaking of induction as induction step as reduction. So usually people say induction mathematics induktion. Usually people say, okay, we'll start with the case n and then go to apply.
I know.
Just for other people also to understand. And here we think in a dual way. So we say, okay, I wish to prove for n plus 1, and I reduce it to n. So that's what the arrow is still. So the arrow is still the same from m to n plus 1. So this is one of the not so many theorems in the course, just for you to say have a solid background of your home task, that it will really make you correct results, and you don't have to check that it's satisfiable if you apply the solutions. And now, just for we will go a bit beyond classical propositional logic, say Boolean logic. This will be needed for our practical class today. So Boolean or propositional logic is too weak for many possible situations. And in order to allow richer expressive capabilities, the more powerful logical languages were introduced. So one of these is first order predicate logic, which is usually used to formalize mathematics. Today in the practical class we'll have some problems on predicate logic with quantifiers. We'll see the results. In Russian it's логика первого порядка, логика предикатов. In predicate logics we have individual variables which range over domain. So it's not Boolean. The Boolean value variables like PQR, they were for truth, right? So it's something which is true or false. Individual variables, they range over objects like natural numbers, something like that. So we have atomic formulae, which are of this form, where P is a predicate symbol, and X, Y, Z are variables. So say X is less than Y, it's a typical predicate, or X is equal to Y. It's a binary one. We have a ternary, for example, that I don't know, that, for example, the mark for a student for a course, it's a ternary predicate. That the mark for student John for course in discrete math is, I don't know, 8. 3 arguments. Denote binary relation. Besides propositional operations, implication, disjunction, negation, conjunction, we also have quantifiers, which are for all and exist. And they are written in this funny topsy-turvy version. Квантор, по-русски, не quantifier, а квантор, не квантификатор. That's an example. Let's read it. So for all x and y, if r of x and r of xy, then exists z, r of xz and r of zy. So let's think about R as being the less relation. So what does it mean? That if you have 2 elements, x is less than y, then there's always something in between. So this expresses the density of the order. So for example, it's true on rational numbers or on real numbers, right? Because always you can take x plus y divided by 2 and it will be strictly in the middle. But for integers, for z, for natural numbers, it fails. You can take just 2 and 3, for example, and there will be nothing in between, strictly in between. So this formula, again, it's satisfiable. There is a model which satisfies it. So there is an interpretation. You have if you think that this means you are talking about rationals, this is true. But it's not universally true, because there exists a model or interpretation where it's false, which is integers. But here the situation is much harder than in Boolean world, because here all these interpretations, satisfiability and stuff like that, they are infinite. So the interpretation is just all integers, all rationals. And by the way, to make this formula true, if you take this as an order, a linear order, which is say irreflexive, you cannot make it finite, because always you have x, y. You need to have a new element in between, again a new element between them, and make the model infinite. And again, universal truth and satisfiability are dual. In Russian, выполнимый, as we know, universally true is общезначимый. It's a strange term which you can see in literature. Общезначимый. So, всюду истинный. Так бы лучше сказать, но термин такой в русскоязычной литературе. And unfortunately, the satisfiability in first order logic and predicate logic is algorithmically undecidable. This means that there is not even a theoretical algorithm for solving it. Without any time constraints, it's undecidable. We will not go into detail. You have to take a logic course to know that, but it's one of the classic studying of decidable fragments of predicate logic, where we restrict our expressivity in order to gain again decidability. And many examples, like the toy example, is say predicate logic where all predicates are unary. So each predicate has only one argument, and this is decidable. It's reducible to Boolean logic. More interesting examples include description logics used in formal ontologies like OWL, SNOMED, CT, etc. And they are systems in between propositional predicate logics, and they're used in knowledge representation. Unfortunately, in this course, we don't have time for discussing this in detail. This is quite an interesting thing, which is on the bridge of logic, computer science, data science. What is the idea here? That you have a database, which is, roughly speaking, some bunch of binary relations, because each object in a database is just a table. The table is a binary function, maybe binary relation, just a Boolean table, or maybe not binary. And the knowledge base is a database which is augmented with some logical structure. So, for example, we know that if A is a child of B and C is a child of A, then C is a grandchild of B. And this could be done as an axiom. And then you can ask the database something like that. So we know only the records of who is his child, who is whose child. And we can ask for, okay, give me all the grandchildren of B. And this is a saturation problem for this database, actual knowledge base, because inside the database, just formally, it does not include anything about grandchildren. It includes only information about children, but also we have the specific axioms which explain what a grandchild is. And using that, we can obtain the we can ask such saturation questions, so satisfiability questions for the database. So it's really used. So, for example, this SNOMED CT is a database for medicine, which uses these algorithms for making diagnosis of diseases. OWL is what's called web ontology language, and the letters are swapped just to make it look like owl, something wise. Well, actually, owls are quite stupid birds, but nevertheless. This is used for modeling web ontologies. Question?
Between propositional and predictive logic, частичный
No, it's промежуточный, probably. Propositional это логика высказываний. Predicate, логика предикатов. Well, actually, these description logics, they use their own specific languages with special connectives called model operators. We're not going to detail. They can be expressed in predicate logics. So we can think about them as predicate logics with restricted use of quantifiers. So this is all the special kinds of formulae allowed. This is all done in order to mitigate the issue of undecidability. If we allow arbitrary formulae like this, then checking satisfiability or universal truth is going to be immediately undecidable, and this will make all the business meaningless. But if you don't do that, you will have this. So, but this again is just a matter of for you to know that such things exist in the world, and if you're interested in that, then you can go into that and read more literature and go to special courses. For description logics in our laboratory of intellectual systems and structural analysis, we have this leading scientist, Mikhail Zakharyachev from London, who is visiting this university also, and this is his topic of research. So you can contact him and maybe do joint research with him. So they, as I said, knowledge bases extend relational databases by richer, logically enhanced language of queries. And of course, this requires fast algorithms, and there is a great trade-off between expressibility and decidability, effective decidability. So this is the end of the lecture. I mean, they probably even did it faster than I supposed to. So questions or comments? Yeah. So again, let me then switch to this course page. All this will be shifted up to current installation. So what is going to happen here? Here you will have, these are what's called materials for homework number 1. What we recommend you to read is that first you will have these examples of Python, Lex, and Yak. So polynomial simplifier. This is the program which takes the algebraic polynomials and simplifies them, reduces to normal form. We have seen examples of this code in some parts of that in the slides. But of course, you will also have this stuff as the full, say, Python code here. You can, maybe we could even open it. No, it's okay though. Close text editor. Yep, so this is the full code. It's not so long. It's just 172 lines, so it's quite simple. And here you see how it works. Yep, so you will. I don't know what this means, but here you have the tokens, and now you have this lexical part. So this is a token for integer. We have discussed it in the class today. These are things which we ignore. These are white spaces, which we just allow everywhere. It's okay. This is the new line, which is just the end of the string, and this is the everything else. So these are the literals, and this is everything else, which we just say this error if we have an illegal character. Now we build the lexer, and then we have some helper functions for working with polynomials. Again, they're self-explanatory. And finally, the interesting part is the parsing rules. So the question is an expression is a term, an expression a minus term, and all this stuff here. Polynomial, and everything here we have this addition, polynomial multiplication, blah, blah, blah. So safe add is safe addition, just not to run out of the array. And finally, if something happens bad, a parsing error, it's a syntax error, which means that something meaningless is given to. Now we import Python lex and yak, and we build the yak thing. And then we simplify polynomials in infinite loop. So the user just is prompted for a polynomial, and then it says, okay, it's an input. And we say that if it's bad, then we just continue. If it's available, we try to parse it. And in the end of parsing, you have this quest, which just says that in the end, just print the result. I will not show how it works, but you can easily see that it should work. So next, we have another example, which is a calculator. The classic example from Aurelius' Lex and Yak book. And here is a bunch of other examples, which just you can look up and see what's there. I don't remember. And if you need more information about parsing, if you're interested in that, there is a book called A Compact Guide to Lex and Yak by Thomas Niemann. I hope that this link works. Let's try it. If it doesn't, yep, it's there still. So if not, I will just put a copy here. So this is the materials on your disposal for homework number 1. Again, if any questions, please ask. And then here you will see what is going on here, how it will be graded. So there's a formulation of the task inside the GitHub, just as, again, we'll do a new clone of the repository, but it's still the same. You will see the formulation of the task formally here. So please read it carefully because it's tested automatically. So if you say mismatch the syntax, the automatic test will fail. So this is an example how a 2CNF should look like. There are technical details, how it should be implemented, so the name of the file, how the function should be named, again for the automatic testing equipment to work. So it has the should return that or none of them. And that you will have the invite link. Again, all of this will be written, especially for the deadline. So again, this is just a standard disclaimer.
How many tries will have?
Infinitely. So you just how did it works? You get invited to the classroom. You get a clone of the basic repository with this README and also some files which will help you to work. Then you try to solve it. When you submit it, then the automatical script starts, which starts checking. If it succeeds, you will see the symbol of success, which is this check. And this means that you are okay. I will see it in my interface, and I will grade you accordingly. So it's nothing, you don't need to inform me or something like that. If it's failure, so it will start with failure, because by default, there is no solution. The test will not work. And then what should you do? You should look inside, because probably the satisfiability check could be okay, right? So there are two parts. And probably one of these is okay. There I will grade it also manually.
This describes first part of forward.
No, they're both of them. So there are two things. You have here you have what? No. You have two of them. So you have what is called. Sorry, it's not the right link. It's formulation. So you see that you should implement two functions. The first is satisfiable. This is what just check for satisfiability. It's the first part. The second is set assignment, which returns you a satisfying assignment. The automatic tests, they check both. So if they all succeed, you did the first, you did your homework number one fully, and you get the full grade, or unless you fail to adhere the deadline. Next, if you do only the first one, then the test will say it failed, but I will see which tests failed. And if all the tests for the first function succeeded, you will get half of the grade. Just easily.
Yes, numbers of the trials. You said that.
Yeah, but if you fail, you can just commit a new version, and the test is
deadline. Yeah.
yes until the deadline. So the tests will run automatically each time you commit to the repository.
Yeah, and by the way, do you see all these trials?
I see all the commitments, so I see the history of the. So technically yes, but I don't. So I will enter the classroom just at the moment of the deadline, just to grab the harvest, to see what happened and what did you. Okay, so yeah, as a fallback you can submit. I will also put I think another email here, but it will be, so all this thing will be put here and it will be renewed. So please do not use this link because then you will get mixed with the students. So or probably it will just say no, it's just closed, something like that. And finally, maybe many of you will ask, while we're on this page, you will see it. So how the grading for the general course is going to be produced. It's 1/2 of the grades for the homeworks, plus 1/2 for the exam. So for the homeworks, first is 4 points, 4 points, 2 points. So it's 10 maximum. And exam is the final exam, also graded from 10 points. And it's obligatory for all the students. So you have to pass it. It will be in the end of the course. Questions?
What will be included in the final exam?
You can see an example here, which this is final exam tasks. It will be not the same, of course, but that's just some theoretical questions. So they will be like that. They will be different, but they will like that. So.
Sorry, where's the theoretical question? Is it?
No, all of these are theoretical. I mean, not programming.
Yeah, that's right.
Yeah, just pen and paper. Yeah, so you can write it. You can print it in LaTeX or something else, all possible. And I think that all the exams will be take home. This is due to the situation that there are people online, and you should all be in equal conditions. So we shall not say have a physical gathering here for the exam. You will just have a day, which is designated by the study office. In this day, you will have, I will publish on this webpage and also on Teams and maybe by email the new programming sheet, which will be like this, but a different one. And you will have time, probably a day, for solving it. And then you just send it by email. And again, you have to adhere the deadlines. So okay, more questions, comments? And the midterm is also going to be like the homework number 2 is theoretical midterm, which will be like this. Maybe it's the same, maybe it will be different, but it's, see, apply a resolution, something, don't know.
So we'll have like one trial to.
Yes, for this will be one trial, yeah. So, but as a usual written thing, so it's. Otherwise, I just will get buried in all these iterations. So the good thing about programming stuff, it's automatically graded. So, yeah, fine, I put it. Okay. So, thanks for listening, and we reconvene in maybe I don't know 15 minutes for the practical class.